We go to a module that actually now is a very transmission in the sense that it's a list of properties that you've got to remember. Okay, they might be derived. Those are the rules. We use Laplace because it's convenient. Laplace has got a certain meaning. From the conceptual meaning of Laplace will follow some rules. Those rules will enable us to do automatic control. Okay, so we do Laplace because it's the tool that enables us to do some computations that are meaningful for us. We don't use Ito's integrals in a basic automatic control because it will be another tool. As I was saying to somebody before, we don't use a brush to screw a nail, to screw a screw. True? So Laplace is a tool for us. So this one should be obvious. True? It's an integral, so integral are linear. This one, we kind of saw it. True? Remember this one, people? 1, 2, 3? Perfect. Remember how to rederive it, okay, from this one. If you apply the what's the name? The definition of Laplace transforms, you get it immediately. Interesting thingy. This one. So this one here comes immediately from the fact that convolution is multiplication. How do I get this thing here through a convolution? If I take f as a signal, and then I take u equals to step, and I do the convolution of this one, it means what? It means doing this thing here. True? Sorry, I was drawing it in the wrong direction. And if f starts from 0, if f starts from 0, 0, I'm drawing it in a bad way. So let's redraw it. Let's assume that we start with an f of t signal in time that starts in 0. So it's f of t, 0, and a signal. Okay, this is my f of t. And then if I do a convolution, f convoluted u, and u is a step, whenever this is now, that is our t, that is this t here, it means multiplying those two, true, and doing the integral. How much are you following, people? 1, 2, 3. So eventually, this one is what? It's f convoluted a step. If I do the convolution in time, it means multiplication in frequency. I don't remember if you remember this formula here. Laplace of e at is going to be 1 over s minus a in the region of convergence. Do you remember this one? Step is E0t. True? Are we together? True? I'm always writing it this way, but I mean for t bigger than 0 and 0 otherwise, it means that this one is the step. Are we together? The step at this point is E0t, that means 1 over s minus 0, that is this one here. Convolution with a step, multiplication in frequency. You see? How much are we together, people? 1, 2, 3. How are we calling this operation here? This is an integration, true? Convolution times a step, it's an integration, true? Integral means multiplying times 1 over s. Indeed, derivative was multiplying times s. True? Do you remember this? Initial condition equal to 0 if essentially this is the derivative. True? Perfect. This one essential. Those ones better if you remember them. Okay? You don't apply them very often. They are just definitions. This is just taking the integral. Okay? Tables, memorize. You can basically think in this way. Sigma omega. A plot that I'm going to use very often is this one. I put a cross here, and this cross might be in -3. Okay? What do I mean? Whenever I put a cross in -3, I'm essentially writing that I've got something that looks like this one, for which s equals to -3 plus j0 makes this one equal to 0. The crosses are where the denominators are equal to 0. Okay? Better? And essentially, whenever you see something like this, these you might think at what? E minus 3t, because this one now it's kind of the inverse Laplace of 1 over s plus 3. Where are you with system theory? With system theory? With Lindsay's? You saw this stuff? No? You saw this stuff? Am I going, okay, am I going too slow, too fast? Okay. Okay. Sigma omega, if I put two crosses here, what am I indicating? I am indicating something that from a Fourier interpretation perspective, it's an E something cosine something, true? It's an E something cosine something, because whenever I put the crosses, it's basically the plus infinity that I was mentioning before, okay? It means that it's for a certain expansion mechanism together, I have perfect match with a certain cosine or sine. Together? Are we together? Perfect. Whenever I put the crosses, it means that I've got E cosine. How much is the E? E is the A, okay? And the omega is the omega, okay? Then, second interpretation that you've got to remember, whenever I put the crosses, it means that whenever I've got those numerator over denominator that I'm going to always use, soon we are introducing them, y, it means that for the s equal to that crosses, I need to have 0 at the denominator, okay? This is the stuff that you will have to remember. That crosses are the roots of the denominator. S minus A squared plus omega squared. This one is shifting, and this one S squared plus omega squared equal to 0. What do I get? Plus or minus j omega. So S equals to plus minus j omega. Whenever I have S plus 3 squared plus 7 squared, where are the roots? Real part has to be minus 3. Imaginary part has to be minus 7. 7, sorry. Do you see? Are you seeing that whenever I write things in this way, I immediately find the real part and the imaginary part of the roots? Are you following me, people? Sorry, here I'm kind of blending in too many things. Probably I'm kind of confusing you. Let's do a recap, because this recap is probably important and you're going to use it for your whole life. So, s plus 3 squared plus 9 squared equal to 0. Roots were minus 3 plus minus j9. True? We see it. Are we together? 1, 2, 3. Because this one makes me having this one, and this one is the solution later. Okay? Perfect. This is first thing that we have to remember. If I write e minus 2t cosine 10t, and this is my h of t, this is an impulse response. In Laplace, where do I have the lines? For which s will I have the line? Sigma omega. I will have for omegas 10, true? And minus 10, true? And expansion factor minus 2. Here and here. Do you see them? Do you see where I put the crosses? It's where the lines are going to be, where I'm going to get matching. How much are we together, people? 1, 2, 3. Perfect. Those crosses are going to be the denominator of my transfer function or a representation of u. Those crosses are going to correspond to something divided by a denominator that has to be equal to 0 for those crosses. Okay? It means that I have to have plus 2 squared plus 10 squared. Together? Question.
No. Why is it negative? Isn't in the integral and the e the Laplace positive, so that it is
E minus st is the stuff that I'm doing. True? So I take this one and multiply times E minus sigma t, and this is the expansion, times E minus j omega t. That is my rotation. Whenever I take this one, minus 2, I put it here, it becomes plus 2. That goes eating away this one. Okay? Remember the minus. Okay? On the left, we're going to have something that expands. On the right, something that contracts. I have an h of t for which my Laplace representation is essentially this one, sigma omega. And this one should be my spring mass system. Is it everything fine, or is there something strange? So everything is fine, something is wrong, I do not know. I have a spring mass system that is my physical spring mass system that will give me my impulse response. My impulse response, somebody gave me the Laplace representation of my impulse response and plots me this plot here where the crosses are here. Is everything okay? Is there something wrong, or I do not know? Something is wrong. Why? Because that process there kind of suggests that my impulse response expands. True? We see it? Can't be. Are there questions? I saw a hand. And in a certain sense, if you remember the stuff here, it's because the Laplace is multiplying E minus ST. The minus is important because in a certain sense, it's eating away. Okay. Laplace, the expansion factor, tries to eat away the natural compression or expansion of my H. If you remember this, you kind of get it out with the signs. Okay, at this point, going back to kind of those formulas, hoping that in this way you will always remember those formulas, I have a certain expansion and frequency. This means I will have a certain expansion and frequency. True? Are we together? That means that my denominator has got to be a certain expansion and frequency. Together? Perfect. And then we have to remember the numerator. Numerator, sine doesn't have the S, cosine has the S. I'm sorry, people. Sometimes life is unfortunate. I still make mistakes and I've got to check it out. The denominator, I get it always right. Whenever I get to the Laplace of sine and cosine, I kind of remember now that it's the inverse. Cosine as S minus A, sine as omega. And actually, this one is the imaginary part, this one is the real part. But this is kind of a refinement. I hope you will remember it. I tend to forget it. For the exam, try to remember it. Okay. This one, we got it. Why I might have made a mess with the slides because there's no sense. It has no sense that we are doing this stuff here. This one is the example that we had before. I think I copied twice two slides and then I made a mess, but it's okay. This one, this is important. This one is important. We are not going to deal with only. We are going to see very soon that we are going to deal with systems that look like t to the power of m e minus sigma t cosine omega t. Those are going to be impulse responses that we are going to get. They are going to connect with the position of the poles. Soon we are going to get it. Whenever we have this object here, it indicates a power on the denominator. Okay? I think you saw it in Lindsay's. Here there's some formulas for rederiving things. I think the most important part, those you can forget. Where is the table? There is a table. I might have messed up a little bit with the slides that I was taking. This one. This one is a formula that you shall remember. And here we might also put the cosine and sine is the same thing here. Whenever we have EAT, it means S minus A. Okay? And if we have cosine or sine, it means this plus omega. Whenever we have a t to the power of n, means normalization factor, but most importantly, a power here. Remember it in this way. People, now I'm giving you kind of a tip for how to remember. Whenever we will draw something that looks like two crosses on the same place, this is going to be not just E minus 3t, but it's going to be t E minus 3t. 3 crosses, square. 4 crosses, cube. Okay? Together? One cross is this one. Are we together on this? One cross this one means that this is a t power of 0. This is the starting point. Every cross that I add is going to be a 1, 1, 1. Okay? You won't mess up. You won't mess up the fact that there's a plus 1 if you remember this. Okay? You see? T to the power of 0 means 1 cross because this one means 1 cross. And this becomes 1. Okay? Together? Two crosses means s minus a, s minus a. Okay, that is an s minus a squared, and it will be a t0 plus 1, n plus 1, 0 plus n. Okay, and whenever you add the cosines and sines, it's the same thing, same behavior. And then there's a normalization factor. This one is not as important, you will see, because somehow the zeros matter there. How are we? How are we? How are we? Okay. Now, let's try to do an exercise just to be together. My h of t looks like this. Sigma omega double cross, two crosses, minus 10, minus 8, plus 3. H of t equals to what? Go. Yeah. Because in a certain sense, it's the curve vertical. For every k, you have a specific point, that point on the closest. So, okay, look at me, look at me, look at me. First thingy, this one, this double thingy here, indicates kind of every cross is a similarity, it's a function for which doing Laplace, that means compressing or expanding and then doing a matching with the cosines, we have an infinite matching, true? Moreover, we have more lines. It means that there's a sum of functions, true? The first one is this one. In a certain sense, I've got minus 8, sorry, minus 8. Those two lines indicate that I have a cosine 3t plus a phase that we do not know because we do not see the angle of the lines, so, times e minus 8t because in a certain sense we are doing a shifted Fourier, true? Shifted of how much? Of a factor e minus 8t, or better e plus 8t, true? If we think about a plus. So this one is this couple. How much are we together up to now? Excellent. Multiplied by what? This number here with this plot here, we cannot know. Okay, this number here might be 10 minus 400, 0.000001. We can't know because from this plot, we do not get the information of how big this function is. Are we together? Then we have another stuff, this one, plus, remember the exercise before, we were having something that Fourier, we were doing like this double, what's the name, spike. It was cosine something plus cosine something, true? We remember this? It's the same here. We have something that is, well, given that there's something here, there must be e minus 10t. But it's a double cross. It means it's a t e minus 10t. Okay? Do we know if it is 10, 15, minus 400, 0.0001? No, we cannot know. Okay? This plot gives us only where the lines, the spectral lines are. Are we together? If I was taking blue and doing 20 times blue, the infinity would be still infinity. True? We would still get a spectral line for omega equals to 10. If we were taking 0.0001 blue, we would still get infinity. We would still get the spectral line in 10, true? If I tell you we have a spectral line in 10, do you know if it is 100 cosine or 0.001 cosine? No. What does this plot give us? Only where the spectral lines are, not just in terms of frequency omega, but also expansion factor sigma. Do we know how big those E alpha t cosine omega t are? No, because I'm telling you just where they are. How much are we together, people? 1, 2, 3. Perfect. And then we see each other tomorrow.